Okay, we're up and running. So I did receive several questions from email. Welcome, Justin. I received several problem requests from email, so I'm going to try to add a few of those. This is just one that I had in there from the past. This is an easy one, right? Because all you have to do is substitute x equals 1. The natural log of 3 plus e to the 1 is just e, and you're all done. So substitution works fine there. So let's take, here's number 65. So number 65 was, let's see, how did they, let me go back. We'll just check it. Number 65. I was just wondering exactly how they worded it. Yeah, okay, so they did have it all expanded out. You see it here on the top. And that's what I've got here on the top line. So you go ahead and square x plus delta x, multiply out the -2 times x plus delta x, and you get this line. And you notice a number of things eliminate themselves. We've got a 2x and we got a -2x. We've got a 1 and a -1, and we've got an x squared and a -x squared. That leaves you with this line. And there, we still have a problem. We still can't substitute because of delta x on the bottom. But notice every term on the top has a delta x, so you can factor it out. And when you factor it out, at last you can cancel, leaving you with the limit as delta x approaches 0 of 2x plus delta x minus 2. And now you can substitute and you get your result. All right, another one, this one was requested, is number 77. Now this one's kind of tricky. The problem, yeah, let me show you the original problem, 77. Okay, it's right over here. 1 minus e to the -x over e to the x minus 1. What's the limit as x approaches 0? Then you can't substitute because e to the 0 is 1, and 1 minus 1 would give you a 0 in the denominator. So you've got to do some kind of maneuver to make that available. And the maneuver, not super obvious, is to multiply top and bottom by e to the x. And when you multiply the top by e to the x, you get e to the x minus, and then what is, I'm sorry, you don't multiply out the top, you multiply out the bottom. What's e to the x times e to the -x? Keep the base and add the exponents. It's e to the 0, and so you literally get this. Let's see, let me get my red here. You literally get this because e to the -x times e to the x is 1, because it's e to the 0 power. And then -1 times e to the -x is minus e to, and then what happens is that can be canceled. And finally, you've got this limit of x, as x approaches 0, of e to the -x, which is 1. So that one, how did I know to multiply by e to the x, e to the -x? That was a tough one. Okay, that's a little bit of a mystery, but anyway, that worked out. All right, now I want to add to that a few other problems. I want to, and this comes from some of the requests. Number 61 was asked about. So let's put that over here on the side. Okay, number 61. Let's change to black. Get rid of my keyboard so it's not in the way. All right, 61 is this. So what's the limit of that? And you can't substitute because of that x on the bottom. So we got to do something with that top in order to get it so we can. And I mean, we can get those together with a common denominator. And what's the common denominator? Well, it would be 3 times 3 plus x, the product of the two denominators. So take both fractions times the common denominator. And in the first fraction, those cancel. And in the second fraction, the 3's cancel. So when you rewrite, what do we have left? On the top, on the left side, we have 3. And on the other side, we have that needs to be subtracted. Okay. Well, that top simplifies, right? I mean, I have to subtract the 3, so the 3's are gone, and I have to subtract the x. So that leaves me with that, and now I can finally cancel. And I get, and now what is that limit? That limit doesn't have anything to do with x, so it's just plain -1. So there's a case where some algebra work allowed us to finish that one up. Another one I want to do is number 63. Did anybody have a question on 61? As long as I still have it up there. Let's do 63 too. And 63 is the limit as delta x approaches 0 of 2 times the quantity x plus delta x minus 2x all over delta x. And we can't substitute, so we've got to do some, and this turns out to be pretty easy algebra here, but we just have to operate on the top, which gives us 2x plus 2 delta x minus 2x all over delta x. By the way, when you're doing work like this, it's really important to carry that limit statement. You know, you don't want to leave, you don't want to just start simplifying. You really need to carry that. All right. So what happens on the top of that fraction? We are able to eliminate the 2 x's. We can cancel the delta x's. And again, we have the limit as delta x approaches 0 of 2, and 2 has nothing, I mean, delta x has nothing to do with that. And so the limit is 2. And that's number 63. So those are at least some of the questions that were asked about. Does somebody want to add another one?
Would you be willing to work through 41, please?
Sure.
Thank you.
Okay, let me find it. Okay, number 41. So we're told that the limit of f of x as x approaches c is 3, and the limit of g of x as x approaches c is 2. So then they ask, what's the limit of 5g of x as x approaches c? Well, the limit of g was 2, so the limit of 5g is 5 times 2, or 10. I just leaned in the wrong place. Whoa. Went to a totally different place. Okay. Let me see if I can get back here. That was not so good. I lost my page numbers, so I can't see them. Wow. So all of a sudden I'm on page 957. Let's go back to the home. Let me try this again. Page numbers are gone. So I'm a little bit stuck here. Hang on a minute. So my page number down here, I can't seem to change it. And I'm sure not going to go paging one by one back from page 956. Let's see. Let's try loading that again. There we go. So now I can at least, except I don't have my keyboard on. Back to page 100. Okay, we're at least close. Is it 2.3? Yeah. We're close. Okay, so here we go with 41. I was going to write on the screen, and that's what caused all the trouble. So 41b, if the limit of f of x is, as x approaches c is 3, and the limit of g of x as x approaches c is 2, then what's the limit of the sum of those two functions? 3 plus 2, or 5. And then part C, what's the limit of the product of the two? 3 times 2, 6. Part D, what's the limit of f of x divided by g of x? 3 over 2. That's really all there is. So thanks to the nicely behaving limit theorems, those things act just as you would hope they would. Okay, that's number 41. You know, I want to make you just reminded me of another thing. You also had, as part of your assignment, these 120, that 121. Let me just take so this true false section here. I mean, make sure you go through those, because those are important too. I just, like for example, number 124. If the limit of something is defined as L, as x approaches c, it's L, then what's f of c? Is that L? And the answer is not necessarily, because you might have a function, as you well know, where there's a hole right at the value, and it still has a valid limit, but because of the hole, it doesn't have a function value there. So that one definitely is false, and the reason is, you know, you might have a hole there. Anyway, I would just like to encourage you, don't make sure you go through the true false 121 to 126, I believe, was assigned to you. Other questions? Okay, well, let's come back here. So here's the lesson for today. Get this thing keyboard off again. All right. So continuity and one-sided limits. And I've got, there's this site called calculus-help.com, which you might want to make use of. It's got some interesting ways to explain this stuff. And so there are a couple little flash videos here that I think do a pretty good job of explaining this. So I'm going to go through those. So here's the first one. What is a limit?
You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now, this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot. So we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height.
So first of all, is everybody receiving the video and the sound?
Good over here.
Okay, good. All right, so let's continue.
Let's start by looking at a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I'm getting very close to the x value of 2, my function is getting very close to the height of 4. There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, negative 2. The hole exists exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of -2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to -2. This begs the question, when exactly does the limit exist? We examine that in the next module.
Okay, so now we ask this question, when does the limit exist? And a new video here.
Now you have some idea what a limit is, and we need to talk about when does the limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x. As long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists. Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually, you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right the right-hand of x, 4 from the left. Note this with a little plus sign in our limit symbol. Our height we arrive at from the left is called the left-hand limit of f of x, as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for it to exist, both the right and the left-hand limits must be equal.
Okay, so I got to come back here. There we go. Let's continue.
Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrived at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph. because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
All right, so let's head back here. So then they ask this question, all right, now that we know when a limit exists, how do you find it?
Once you can determine whether or not a limit exists, the next logical step is to try to figure out what the heck that limit is. So that's what we'll be focusing on in this section. How do you find a limit? The fancy word for finding the value of a limit is evaluate. So when you see the directions evaluate, basically you should be expecting to get a numerical answer. There are three major ways to evaluate a limit. They are substitution, factoring, and the conjugate method. We're going to go ahead and start with the easiest one, which is direct substitution. It is just as easy as it sounds. We'll take an example. Here's one. The limit as x approaches 0 of the fraction x squared minus 1 divided by the quantity 2x plus 3. In order to evaluate this limit, all you've got to do is plug in 0 everywhere you see an x. So we'll put in 0 in the numerator and in the denominator, and we end up getting negative 1 divided by 3. So our limit is negative 1/3. It's as easy as that. Unfortunately, not all limits are this easy. You've already seen one for which that's the case. Remember that function that we were dealing with in the first section of this chapter? In case you don't, here it is again. The limit as x approaches 2 of the fraction x squared minus 6x plus 8, all divided by the quantity x minus 2. We looked at this before. It had a hole in it at the coordinate 2, negative 2. And we concluded from that the intended height was negative 2, making it the limit. However, it would be nice to be able to figure out why this is true mathematically. And to do that, we'll have to use the factoring method. As you can see, and as we saw before, direct substitution results in 0 divided by 0, which is not allowed. So we'll have to resort to this new method. We'll use the factoring method because the numerator of this fraction is factorable. If we factor it, we'll get x minus 4 times x minus 2. Can you see why that's a good idea? Well, the reason is because now the numerator and the denominator both contain the term x minus 2, which I'm going to cancel out. This leaves the limit as x approaches 2 of x minus 4. This is much simpler to solve because now you can use substitution. And when I do, I get 2 minus 4, which is equal to negative 2. Remember, we knew the limit was going to be negative 2, and we're right. Feels good to be right. If the substitution method fails and the factoring method fails, you're not without hope. You can still try the conjugate method. Before we talk about the conjugate method, though, we might as well figure out what a conjugate is first. Take a look at this expression, the square root of x minus 4. Now, this is a plain old two-term expression. However, it is easy to make a conjugate. All you do is change the negative sign in the middle to a positive sign. The conjugate of the square root of x minus 4 is the square root of x plus 4. That's all there is to it. Now, what if you see an expression like this in a limit problem? For example, this limit problem. The limit as x approaches 16 of the fraction, the square root of x minus 4 divided by the quantity x minus 16. Well, what we'll do is multiply the top and the bottom of the fraction by the conjugate of the radical expression, which, as we said, was the square root of x plus 4. Now, the magic of this is that as you multiply out, the numerator will actually become x minus 16. You don't want to multiply the denominator out. Leave them as separate factors. Since I have x minus 16 in both the numerator and denominator, I can cancel them, just like I canceled like terms in the factoring method, and I'm left with the limit as x approaches 16 of 1 divided by the square root of x plus 4. Do you see why we didn't want to multiply out the bottom? It makes simplification much easier. Now I'm able to plug in 16. Substitution works. When I I do so, I get 1 divided by 8. So the limit as x approaches 16 of my original function is 1/8. And that's the conjugate method. There you have it. There are 3 major methods to evaluating a limit. Substitution, which is the easiest. Factoring, which is useful when either the top or the bottom of the fraction is factorable. And the conjugate method, which is useful for radical fractions.
Okay. And then we just have one more video to look at. What makes a function continuous?
Calculus relies heavily upon the existence of what's called continuous functions. In fact, most of your important theorems include a prerequisite that any function in question must be continuous before you could even think about applying the theorem. For example, the intermediate value theorem, which we'll also learn in this chapter, requires that the function be continuous. Well, in theory, continuous functions are predictable functions. They have no undefined points, no breaks, no holes, no jumps in the graph. But enough talk. Let's take a look at some pretty pictures. Now this function f is continuous, but these, g, h, and I, they're not continuous. Each of them, in fact, is discontinuous for a different reason at the x value of x equals c. Now this one, on g, you've got a little hole in the graph. That's called point discontinuity. Over here on h, you've got a vertical asymptote that breaks the graph. Now this is called infinite discontinuity. And finally here on graph I, you've got a graph that just plain snaps in the middle. And that's called jump discontinuity. Now how can you judge just by looking at the graph of a function if it's continuous or not? Well, a continuous function makes a good bridge. Now see, if I drive across the graph of f, it holds up nicely. Whereas if I try to drive across the graphs of the other functions, I might fall through or fall off. So, continuous functions are predictable. But what does that mean? Well, it means 2 big things. 1, no breaks. Well, we already know that breaks occur in functions where no limit exists there. Therefore, for a function to be continuous, it must have a limit at every x in its domain. Secondly, no holes. Continuous functions must be defined everywhere in their domain. Mathematically now, we say that continuous functions have this property. For every x equals c in their domain, the limit as x approaches c of f of x is equal to f of c. In other words, not only does the limit exist at every point, but the height the function reaches for every x matches the limit. How can you tell if this happens? It seems pretty complicated. It's actually easy. If you can evaluate any limit on f of x using only the substitution method, then the function is continuous. And that's all there is to it.
Okay, in the meantime, I got I got a question via email, so we'll come back. I just wanted to show, let's see, evidently somewhere up here on the top. So when I did number 61, okay, did I do something wrong up here? We do the 3 times 3 plus x. I multiplied by 3 times 3 plus x. I got 3 minus 3 plus x. Okay. Yeah, I think I'm going to have to follow up whoever sent me that email. It doesn't look like I did anything wrong here. I will have to follow up with you. on that one. All right, so let's go back now. All right, example. So here's an example of a function where obviously it's discontinuous. You can see that the right-hand branch of the graph does not meet the left-hand branch of the graph, and therefore what? The left-hand limit is 1, the right-hand limit is 3, and you know that when the left and the right don't agree, that limit does not exist. Okay? So, I mean, I taught you that before, so that's not new. So one more time, try substitution first. Can you do it? If so, rejoice. It works beautifully. Go ahead and do it. And here you can see it does. Can you plug in 2 to this? Yeah. And you can see that you're going to get 6 minus 1 or 5. So that's all there is to that one. So here's number 53. It's an example on page 53, excuse me. So, so when you do this, you can't substitute, right? And so what you're going to have to do is you're going to have to do some factoring if possible. Can we factor this? And here comes that difference of 2 cubes that I taught you how to factor yesterday. Again, repeat the limit, otherwise it's illegal. The cube root of x cubed minus 8 is the cube root of x cubed, x, minus the cube root of 8, 2. The other factor is a trinomial, x squared, and then on the end here you've got 2 squared, and then you've got negative 2x, and you've got to change the sign on that. So that's the factorization for the difference of 2 cubes again. All right, now a wonderful thing happens. That 2 that's on the bottom, that creates all the problems and means you can't substitute, now cancels. And so, just to repeat, we now are doing this problem. And now, go ahead and substitute. Works just fine. So you get 4 plus 4. So we basically get what? 4 plus 4 plus 4. And you actually know the limit. And then, of course, we've got the conjugate problem. Let's do another one of those. So you can't substitute because that creates 0 in the denominator. So we have to do something, and we got to get that x out from underneath that square root, so there's at least a hope of canceling with that x. And the answer is you can do that by multiplying the top and the bottom by the conjugate. You know, the conjugate, the opposite sign in the binomial for that second number. And of course, I have to do it on the bottom too. So on the top, well, let's do it down here. So on the top, we now get square root of x, you get that first term squared, which removes the square root. Praise the Lord. And then on the end, you get the difference of that square. And like they said in the video, don't multiply this out. Leave that denominator. And then, of course, on top, you get x. And this cancels. You get a 1 on the top. So we're down to this situation. And now you can substitute. go ahead and plug in x equals 0. And you get, you know, the square root of 4, which is 2, and 2 plus 2 is 4. And you can calculate your limit. So then you get problems like this might present themselves. So number 44 says, is the function ever discontinuous? If so, where? And what type of discontinuity do we have here? Well, you can see that when x squared equals 4, that creates a 0, and we know that that can't happen. And in what two cases would x squared be equal to 4? When x is a plus 2 and a minus 2. What kind of a discontinuity? Those would be asymptotes, okay? So at -2 and plus 2, you would have asymptotes. Here, let's just take a quick look. Need my keyboard again. So what did we have there? X over x squared plus 4. Or was that minus 4? Minus 4. And you can see we get 2 at x equals -2, we get an asymptote. At x equals +2, we get an asymptote. What kind of discontinuity is that? That's infinite. That's called infinite discontinuity. All right, so that would be the answer to that question. Number 49, likewise. Now, is this function ever discontinuous? Yes, when x equals -7, we have a 0 in the bottom. What type of discontinuity is this? Well, let's just take a quick look. Absolute value of x plus 7 over x plus 7. So what happens is you literally get one of these left-right disagreement graphs here. Okay, so in other words, never the twain shall meet. And so what do we call that? All of a sudden I can't remember. That type of discontinuity. I just can't remember the type. Let me
Jump, is that it?
Thank you, that's jump. That's exactly correct. All right, and then the last one. Just take a look at this problem. What value of a function makes the function continuous? So sometimes you're going to get a piecewise like this. And it says, what value of a will make this discontinuous? I'm sorry, will make it continuous. And the answer is when 3x squared equals ax minus 4. And so you literally can find out by setting them equal. And then you can go through and you can I didn't finish it. You can get it to the point where you can find out, you can solve for a. So the last step here would be just to continue. Now let me move this up a little bit. So you can just continue this and say negative a equals -4 over x minus 3x, and then multiply both sides by -1. And that's when a is equal to that value. So you'll see a problem like that, I believe. Let's take a look at number 77. Here we have, okay, on what intervals is this function continuous? And so the question is, when might that denominator be equal to 0? And, well, you know, if you can't tell, you can always go in and find out by saying just set it equal to 0 and find out when that terrible situation would occur. And you could either use the quadratic formula or you could try factoring. And this one factors, right? I mean, this one does not factor. You can't factor this. So we could use the quadratic, x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. You could certainly do that, and then you'd know. All right. Questions? Any questions that you would like to bring up? I'm trying to look at my different devices here. Yeah, I got Abby, I got your message, and I don't know, I'm going to have to answer that tomorrow. And maybe I copied the problem wrong, I don't know. But we'll take a look at 61 tomorrow. Anybody else have any questions? So we're on 2.4 here. So those OPT right here means you don't have to do those, but you know, be kind of cool if you could do them. All right, that should be it then. Thank you for your attendance and your participation and for straightening me out in some cases. Thank you.